Yeah. So the first speaker will present the second session is Professor Choi from the Chungnam University. And he will talk about the probing sterile neutrino matter in the PTOLEMY-like experiment.
Okay, thank you for the invitation. So my talk today is how to probe the sterile neutrino dark matter. Actually, this work is now in the archive, this number, and with my students at the program and Sungmun. So yeah. So this is our galaxy, Milky Way. Actually, we know that around our Milky Way, there is a dark matter. So dark matter, like this is a white one is visible, our galaxy with these stars and kind of things. This blue means actually we cannot see the dark matter, but we believe that there must be some dark matter there to explain the rotation of this our galaxies, and also many astrophysical observations is there. So to observe dark matter is one big our mission, and another one is there also must be neutrino background, so like a cosmic microwave background, which is decoupled from the early universe. In the same way, neutrino was in thermal equilibrium in the early universe and decoupled at some time around temperature of 1 mega electron volt, and exists just around in all the universe. So still also we didn't observe this neutrino background, but we believe that this cosmological neutrino should be around, I mean, just moving around our galaxy. And another one is, now this is beyond the standard model, sterile neutrino. Sterile neutrino is well, similar to neutrino, but neutrino, there in the standard model, there are 3 kinds of neutrino, but this is extra. Extra sterile neutrino, maybe if they exist, I mean, in the model, in the universe, then sterile neutrino, I mean, similar to this standard model neutrinos, sterile neutrino also may exist in our galaxy, in the universe. So that's the assumption in this paper. If sterile neutrino exists, and then maybe dark matter, or then maybe, if it is cold, it can be dark matter, but if it is warm, the mass is small, then it can be warm component. Anyway, so people trying to observe this neutrino and also sterile neutrinos using some tritium beta decay. So here in this work, we are just study how much we can probe these sterile neutrinos, cosmic sterile neutrinos, which are around in our galaxy using this experiment. So that's the main point. So basically like this, the usual beta decay. Beta decay is some nuclei decays to lighter nuclei and produce electron and the neutrinos. That's a natural beta decay without any energy barriers. But if the neutrino around this nuclei collide with this nuclei, then this nuclei changes and produce electrons or positrons. So this interaction we are considering. Actually, this neutrino can be cosmological neutrino around our galaxy. So because it has some kinetic energy and also mass, then this mass is transferred to the energy of the electron. Okay. So this energy spectrum, if we see this spectrum, energy spectrum of electrons, then maybe we can distinguish this neutrino, initial neutrino, or some kind of things. But that's the neutrino. But if there's a sterile neutrino, and also if sterile neutrino has a mixing with the electron neutrinos, well, this X means the mixing, then sterile neutrino also can interact with the, can be captured by this nuclei, and then this electron is produced. Then this also can affect the spectrum of electrons. That's different from the standard model neutrinos. Okay. So this spectrum depends on the mass of sterile neutrino, actually, mass. And also the size of mixing. So mixing is usually much smaller than 1. So this interaction rate, sterile neutrino capture rate should be smaller than the electron neutrino capture rate. So that maybe we can just expect it's more difficult to prove this sterile neutrino. So maybe. But also it depends on the number density of the neutrino or sterile neutrino in our galaxy. But this number density, I mean local number density for sterile neutrino can be larger than electron neutrino. So then maybe this small mixing can be compensated by this large number density. So finally, I will show you later. Then maybe in some model or in some parameter space, the sterile neutrino maybe capture rate can be larger than standard model neutrino electrons. So that's the final result. Okay, so I'll give you some introduction about this experiment. Anyway, neutrino, in the standard model neutrino, we know these weak interactions. So in the standard cosmology, we can calculate the relative density of neutrino. So if neutrino is now non-relativistic, then at the present, the relative density is just the proportion to the mass. And if we consider the upper bound on the sum of the mass from this Planck satellite, then should be smaller than 0.12 electron volt, then neutrino relative density is much smaller than dark matter density. So neutrino cannot be dark matter. And also because neutrino mass is small, then the free streaming rate is maybe larger than the galaxy size. So this is another reason the neutrino cannot be 100% dark matter. So we need another cold dark matter. And this standard model neutrino can be just a hot component of relic particles. And actually, the number density is around 112 per cubic centimeter for one flavor neutrinos that exists in our universe with some velocity around 10 to the 3 kilometer per second for 0.1 electron volt. So it's quite non-relativistic at the present, actually. And that's the cosmological neutrino. And actually, we don't know the exact mass of the neutrino. So one project to measure this absolute mass of neutrino is that this kind of beta decay, using beta decay. So beta decay using tritium decay, and that produce electron and the antineutrino. Usually this beta decay, the energy spectrum of electron is kind of this continuous spectrum because there is an additional neutrino. But this endpoint, that depends on the mass of neutrino, because when the mass of neutrino is 0, massless, then the spectrum of electron follows this blue line like that. But neutrino has a non-vanishing mass, then the energy of electron can be reduced by this amount of the mass of a neutrino, because this energy difference, mass difference of this tritium and the helium-3 goes to the mass of neutrino and also energy of electron. So this, when for example, neutrino electron to mass is 1 electron volt, then that the energy spectrum of electron follows this red line. So this endpoint is decreases by 1 electron volt. That's basically the mass of the neutrino. So by measuring this difference very precisely, then we can measure the mass of the neutrino. But for this one, then the precision, the resolution of energy should be very precise. Maybe should be smaller than the mass of the electron neutrino. In that case, we can measure. But actually, and like this, the resolution is something like that. I will explain more. So anyway, in the Catherine experiment is one experiment for that. Something they produce this tritium and then tritium decay and produce electron and measure some energies. So last year, actually, they announced a new upper bound on the mass of neutrino is should be less than 0.8 electron volt. So this is for this electron neutrino. There is some combinations, but so this is now upper bound on the mass. But anyway, maybe they say in 5 or 6 years with more data, then they can be, the bound can be lowered down to 0.2 electron volt. So if the neutrino mass is larger than this one, then they maybe see this measure, but anyway, you have to see. That's the neutrino mass measurement. Anyway, with the same experiment, we can measure this cosmic neutrino, cosmic electron neutrino. Because this dashed line is the energy spectrum of the electron when the neutrino is massless. If the neutrino is massive, the endpoint moves by the amount of this neutrino mass to the lower energy. But if there is a cosmic neutrino, the neutrino is interact with the tritium and also produce electron. That is additional interaction to the previous natural beta decay. So in this case, electron has a additional energy from the mass of neutrino. So energy spectrum, they can make some peak of this, the red line. That position is exactly the same as the mass of neutrino, because this neutrino is non-relativistic, so they can make a peak. So if we can observe this peak, well, then maybe we can say that we measure the cosmic neutrinos. But also this one, to observe this one, this mass is now smaller than 0.8 electron volt, then the resolution should be much better than this mass of neutrinos. So still we didn't see anything in the experiment because the resolution is not that good enough. Yeah, something like that. But in the future, like Catherine, some people suggest that Ptolemy-like experiment with better resolutions, where, for example, data is a resolution is a 20 milli-electron volt, so 0.02 electron volt. Then maybe we can measure this spectrum mass of neutrino maybe around this value. This is some simulation of the spectrum measuring these cosmic neutrinos for normal hierarchy, normal ordering, or inverted ordering. Anyway, this peak can be shown like this. Okay. Anyway, there's a future experiment, and their prospect in this Ptolemy-like experiment is like that. This mass of the lightest neutrino mass, 100 milli-electron volt, and this is a local neutrino number density. Local means so neutrino number density around the solar system, around the Earth actually, because massive particles can be localized in the galaxy. So then the number density can be enhanced compared to the average in the universe. But I will explain more later anyway. So they show this kind of sensitivity for observing this standard model neutrinos. But actually what our interest is that it's not the standard model neutrino, it's a sterile neutrino. That's additional. The sterile neutrino is a sterile actually at its sense. Usually in the standard model, neutrino is massless. But we know that the neutrino oscillations requires, to explain neutrino oscillation, we need to give a mass to the neutrino. So one of the simplest way is, anyway, we introduce additional right-hand neutrino, and then right-hand neutrino is a singlet, so usually it can have this Majorana mass. Then one of this, then in that case, this left-hand neutrino can have the Dirac mass, and also this right-hand Majorana mass. Then this mass matrix, diagonalize this mass matrix, then we can give some very light mass to the neutrino. When the Majorana mass is very large, then it's called some system mechanism. Anyway, so in this case, this sterile neutrino can have a mixing to the active neutrinos in the mass eigenstate. So here, the theta is the mixing angle between sterile neutrino and the active neutrino. There's something like a relation. So this sterile neutrino and the flavor eigenstate is interaction, have only Yukawa interactions, but after this mass mixing, mass eigenstate also can have mixing with the sterile active neutrino. So this sterile neutrino, it cannot be stable. It can decay to the 3 neutrinos because sterile neutrino distributed in US has a mixing to the neutrino and it can decay to lighter neutrinos. And also this sterile neutrino can decay to neutrino and the photons. So usually, some massive sterile neutrino can have a signature of X-ray signal at the present universe. So many people actually studied this sterile neutrino as a dark matter component possibility, as a candidate of dark matter, or to explain some anomalies in the neutrino oscillations. Anyway, this sterile neutrino has this interaction in the early universe. It can be produced. So usually the standard produced through this oscillation with active neutrinos. So that is called this Dodelson withdrawal mechanism. So it's a typo, SON is missing. So Dodelson withdrawal mechanism. So basically, the neutrinos, active neutrinos are thermal equilibrium in the universe. And also from this active neutrinos, sterile neutrino is produced, so mixing, then sterile neutrino is usually interaction is very weak, so it's just remains in the universe. So they calculate this relative density of sterile neutrino at the present time is around 0.2. For the mixing angle squared is around 10 to the minus 9, and the mass of sterile neutrino is around 3 keV. So for this parameter, for keV sterile neutrino and the mixing angle 10 to the minus 9, then this sterile neutrino can be explained the relative density of dark matter. So people studied this kind of things. And also another one is if there is some lepton asymmetry, then this relative density can be enhanced due to some resonance. So that is causes some Shiffer mechanism. Maybe. And also NUS can decay to 3 neutrino. Basically, well, we have to solve this Boltzmann equation actually for sterile neutrino. Fs is the distribution function of the sterile neutrino. H is the second term is due to expansion. The right-hand side is a sin square 2 set time. Set time is mixing between sterile neutrino and the active neutrino. It's a proportion to the mixing. And gamma is the production rate of the active neutrino actually. So active neutrino produced and due to mixing, so sterile neutrino number density is produced. And this mixing actually depends on zeta m. M means in the matter. Because in the early universe, there are many matter components. This zeta, usually like MSW effect. So in the matter, there's additional contribution from potential in the matter. So in this case, this potential comes from these weak interactions and kind of things like that. So I mean, this potential actually proportional to the temperature force. So temperature is very, very large. Then VT absolute value becomes very large and mixing is suppressed. So actually mixing becomes a zero. So actually high temperature, the sterile neutrino is not produced. So relatively some small temperature, now when VT becomes small, then this sort of mixing sterile neutrino is produced. So actually the maximum production rate happens at the cosmic, temperature is around 100 MeV. So temperature is much larger than this T maximum, then sterile neutrino is not much produced. And at this temperature, most of them are produced. Or below this temperature, also the production is also becomes less and less suppressed. So anyway, people usually show this kind of plot for the sterile neutrino as dark matter. So this is the mass of the sterile neutrino around the 1 keV, 5 keV, some 10 keV. So this is the mixing angle sin square 2 zeta. So here, this red one is constrained from X-ray because sterile neutrino decay produces the photons, gamma of X-rays. So it's ruled out in the red region. And this small mass of sterile neutrino, well here, we're assuming that the sterile neutrino 100% dark matter, then because of neutrino is a fermion, so the mass should be larger than around the keV because of the phase bound. And for this Dodelson withdrawal mechanism, then this line, NRP, gives 100% of dark matter. For smaller mixing angle, then number is reduced. Larger than 1, then there's a 2 overproduced sterile neutrino. So usually, so this black line, then the sterile neutrino can be 100% dark matter. But another problem is that there is this Lime alpha constraint that is due to the warmness of dark matter. So that gives usually bound is around 5 keV, some 10 keV, depending on some papers. So this usual Dodelson withdrawal mechanism actually all is disfavored from this Lyman alpha. However, people consider that this lepton asymmetry, the Shiffer mechanism enhances the relative density. Then in that case, this reason can be still available. Then in that case, sterile neutrino mass is larger, like that. So this is a dark matter of sterile neutrino that exists around our galaxy. So for this sterile neutrino also can be searched in the beta decay of a tritium. For example, this is not the cosmic sterile neutrino, just the sterile neutrino, because tritium, this nuclei also can decay and produce sterile neutrino, addition to the active neutrinos. In that case, it's different because this red line is some just standard without the mixing to the sterile neutrino. Then with the sterile neutrino, this shape changes. Actually, the left one, we can see that the 3 neutrino model is this blue line. But when there is a sterile neutrino with the mass 400 electron volt and the size square set is 0.01, that's somewhat large. But in that case, this relative ratio is reduced at the high energy spectrum. So if we can measure these differences with high resolution of energy, then also we can see sterile neutrino in the beta decay experiment. Actually, from Katrin data, they announced this year, July, then the constraint on the mass of sterile neutrino and the mixing to the electron neutrino. So they exclude that this, well, depending on how to exclude something, this kind of red line or blue line. So they actually disfavor for the masses around 0.1 to 1 kilo electron volt, mixing angle around 10 to the minus 3. So that's the new result for the constraint on the sterile neutrino mixing to the electron neutrino. So that's the introduction. So this is our work now. Our work is then how to measure cosmic sterile neutrino, not the cosmic. For this one, the sterile neutrino depends on the number density of sterile neutrino in our local solar system. But actually, for the number density in the our local universe, I mean local around our sun, is different from background density because due to the gravity of our galaxy, the neutrinos can be gathered down. I mean, density can be enhanced in the center of the galaxy. So this is one paper. This is for neutrino, actually, neutrino mass and the radius from the center of our galaxy. So if the neutrino is around 0.6 electron volt, then in the center, this n pi is the cosmological average density of neutrino. So nu is the number density in the galaxy. It's enhanced by factor 20 times for mass around 0.6 electron volt. However, neutrino mass is 0.15 electron volt, then the enhancement is less than factor 2 because for small mass, the velocity is much larger, kinetic is large, so it's difficult to be captured in the galaxy. So that's the reason. But mass is large and larger, then more density is enhanced. So actually, for usual cold dark matter, it's very non-relativistic. The enhancement is 10 to the 5. The dark matter density in our local solar system, the density is larger by 10 to the 5 factors around that compared to the background density. Anyway, because we consider sterile neutrino mass around some electron volt to some 110 keV, so we need to know this how much they are captured. The local density is enhanced. Actually, this needs to do some big simulations. We didn't do that. We just followed this paper. Here is 2 papers, and here the local number density of sterile neutrino, and NS is the cosmological average. Then this FC is enhancement. So enhancement FC is like that, depending on mass. Here is some 1 electron volt, 10 electron volt, some 100 electron volt. So for 100 electron volt, then it's around 10 to the 5 enhanced. But the one less than 0.1, then no enhancement is like that. So if we consider, then yes, we can measure this sterile neutrino. Also, that gives us this kind of peak spectrum. So actually, we calculate this and then show you the result. So this is for the standard Todelson-Wheeler model. Then the number density of sterile neutrino is fixed by this model. In that case, also there are many other constraints. So important constraint is CMB. constraint from this, and also Lyman alpha because it's a warm dark matter. So in that case, consider then these numbers means the capture rate per year, considering the 100-gram tritium. In that case, we find that the maximum is around the 0.10 to the minus 2 or 10 to the minus 1 event. So maximum is a 0.1 event per year. So that's very difficult. We say that it's difficult to probe this sterile neutrino in this model, 도대성 withdrawal model. So this is a constraint. I will explain more. Okay, it does not move. Stop. Yeah, anyway, so main point is that, so using in the standard Todelson withdrawal mechanism, the relative density is fixed from that. And then in that case, the capture rate of sterile neutrino is less than 0.1. So it's quite difficult to observe. But we found that some model of the early universe changes. For example, the reading temperature of the universe is smaller than 100 mega electron volt. 오, 되네요. 여기서 안 넘어가네. 아, 끝이 아닌데. 다시 볼까 이걸로? Show you just the final result. So I mean the relative density of sterile neutrino depends on the zeta squared, the mixing squared, and the gamma. Gamma was this interaction rate. So I mean this interaction rate becomes small, then zeta squared can be enhanced with the same amount of relative density of sterile neutrino. That's what we do. So I mean the reading temperature is the maximum temperature of the early universe after inflation or some things. So this reading temperature may be so reading temperature is smaller than this maximum temperature. Maximum temperature, I said around 100 MeV. So temperature larger than this Tmax, then the mixing suppressed the matter. And temperature smaller than Tmax, also the rate is suppressed. So we assume if the temperature, read temperature smaller than Tmax, then the sterile neutrino cannot be produced enough because most of them actually produce Tmax. But the highest temperature is smaller than this one, then the relative density just depends on the reading temperature because it's suppressed compared to the Todelson withdrawal. So in that case, to explain the dark matter density enhance, then we need to enhance this mixing. U equals is zeta squared. So we need to enhance this one. So for example, reading temperature 5 MeV, then mixing squared can be 10 to the minus 3. In that case, omega can be around 0.5. But now the mixing is very enhanced. Previous one was 10 to the minus 9, but now it's 10 to the minus 3, but with the same amount of density. So because the density is the same, all the constraints from this Lyman alpha CMB is just the same. And they move to the larger value because previously this CMB and Lyman alpha constraint located around 10 to the minus 9, but now they moved to higher values. Higher values, something is like that. So now then the capture rate can be enhanced to 10 events per year, 10 events, not the 0.21. So if it is 10 events, then now maybe it's possible, maybe hopefully we can see in the experiment. That's for reading temperature 5 MeV. Well, another model is reading temperature maybe can be very large, but phase transition can be lower than this 100 MeV. So TC means that the Majorana mass may be generated by some vacuum expectation of some scalar fields phi. So when this phi has a value, that can give the mass of the Majorana neutrino. In this case, the TC for phase transition may be smaller than this maximum temperature. In that case, then also this rate density depends on TC, not the TR. It's very sparse again. So in that case too, well, we can find some 10 events per year. So as a final summary, so usual Bodson withdrawal mechanism, when the temperature of the universe is high, then it's difficult, basically impossible to probe this sterile neutrino. Well, that's also similar to electron neutrino is not easy to probe. But if in different scenario of early universe, for example, low reaching temperature or phase transition happens very late, in that case, the relative density of a sterile neutrino can be same, but the interaction, the production rate is depressed, suppressed, but mixing can be enhanced. In that case, we can find that the larger capture rate of a sterile neutrino in the future, maybe very far future, but in the future, we can detect some 10 events per year. So it's very promising, but still sterile neutrino cannot be enhanced. Sterile neutrino, active neutrino is still some 0.1 events per year, but sterile neutrino can be larger than that by factor of 10. So yeah, so we can study this one. Okay, that's all in my talk. So thank you very much.
So are there any questions?
Thank you for your nice talk. So in the case of low reading temperature, you require the size of a mixing angle for dark matter abundance. Is it consistent with the X-ray constraint? With this large mixing angle, it's consistent, the X-ray.
X-ray bound is a very large mass around the KV. We consider around the 10 electron.
10 electron.
Yeah, here is, I mean, here we are focusing around here actually. So it's around the 10 electron volt. So X-ray bound is larger than KV, so it does not relevant.
I see. So this is not clustering.
Yes.
Okay. So another question is, you briefly mentioned about another mechanism.
Yes. To
produce dark matter abundance. The phase transition you mentioned.
Yes.
What is the phase transition about this?
To generate the mass of this Majorana mass. Because TC temperature larger than this TC, then this sterile neutrino has a mixing. There is no Majorana mass. So in that case, there is no mixing. But there is only this
mixing is generated.
Also there is a Dirac mass and Yukan interaction. But through that terms, the production rate very suppressed. So here is the second one, actually the calculation. So in that case, it's suppressed by 10 to the minus 9. So it's negligible.
I see.
But below TC, then now it's through mass mixing, the standard calculation. So that's what I mean.
Okay, I see. Thank you.
So, yes.
Thank you for my talk. I have a basic question. I think there is a new measurement of the rates of uranium-235, if I recall correctly, by stereo collaboration.
Yeah.
And they claim basically that it should have some impact on sterile neutrinos.
Impact on sterile neutrino from what? Sorry,
yeah, on sterile neutrinos that basically mix with the standard modern neutrinos. They even claim that basically some of the models can be even excluded.
Some of the models?
Yeah, stereo collaboration. I think it's like 1 month or 2 months ago.
Yeah.
Do you have some comments about the impact of these measurements?
So which experiment? I don't know.
Stereo collaboration. Yeah.
I don't know. Yeah. Anyway, I can ask you again after.
Yeah, okay.
This. Okay.
So is there any question from the online participants or an audience? If not, let's thank the speaker and let's move the second speaker from Sogang University, and he will give us talk about the dependent bound on the non-relativistic theory of WIMP-nucleon scattering from gravitation and string observation. So,
Today I will talk about halo-dependent bounds on the non-relativistic effective theory of WIMP-nucleon scattering. This talk is based on our recent work, which is in collaboration with Professor Stefanos Kopel and Dr. Chung-Ang. As we know, cold dark matter is believed to provide the 25% of the energy density of our universe, however, detected so far only through gravitational effects. WIMPs are one of the most popular candidates for cold dark matter. A popular technique that is used to search for WIMP is direct detection, whose physics is mainly based on scattering of WIMPs against nuclear targets. Same WIMP nuclear scattering can trigger gravitational capture of WIMPs in celestial bodies like Sun, where these captured WIMPs can annihilate themselves to produce neutrino signal. Neutrino telescopes searching for this kind of signals can also constrain WIMP scenario. Estimated WIMP signal for both direct detection and neutrino telescopes depends on the velocity distribution of local WIMPs. Now, non-detection of any new signal in direct detection or neutrino experiments put upper limits on the WIMP nucleus interactions. While predicting WIMP signal for these kinds of experiments, two classes of major uncertainties arise. One for the nature of WIMP nucleus interaction, and another one is the for WIMP speed distribution in the solar frame, which determines the incoming WIMP flux. For WIMP nucleus interaction, the most common choice has been either standard spin independent interaction or standard spin dependent interaction. And for WIMP speed distribution, the most common choice has been standard Maxwell-Boltzmann speed distribution in the galactic frame and then boosted to the solar frame. This is called standard halo model. And this U is the speed of WIMP with respect to solar frame. Now, this Maxwell-Boltzmann distribution is a zeroth order approximation to the WIMP speed distribution in our halo. Numerical simulation of galaxy formation can only tell us about the statistical average properties of dark matter halo. However, several merger events can add sizable non-thermal components to this speed distribution. Also, growing number of observed dwarf galaxies in our Milky Way indicate that our halo may not be perfectly thermalized. Due to all these reasons, one needs some halo independent approach. The strategy is to basically to find the most conservative bounds on the WIMP-nucleon interaction depending on the null searches of the detector, with only constraints that the local WIMP speed distribution is normalized to 1, where the WIMP speed distribution can have any profile. However, we know that direct detection experiments are only sensitive for a WIMP speed that is larger than some threshold value. This threshold speed is corresponding to the recoil energy threshold of the detector. Hence, direct detection alone cannot probe the full WIMP speed range, and so halo-independent method cannot be applied with direct detection alone. Because if I have a WIMP speed distribution that is concentrated below this threshold value, the signal rate for direct detection will be 0. However, capture of WIMP in Sun is more favored for low WIMP speeds. Incoming WIMP particle, after being scattered against the nucleus inside the Sun, will be gravitationally captured if its velocity after scattering is less than the local escape velocity inside the Sun. Otherwise, it is difficult to capture them. That's why low wind speed particles are more favored for capture. After being captured, these WIMP particles continues to scatter against the nuclei inside the sun and ultimately settle inside its core, where they can annihilate to various standard model particles and ultimately give neutrino flux, which can be observed through neutrino telescopes. Now, since direct detection experiments are more favored for high wind speeds and limit from capture or neutrino telescopes are more favored for low wind speeds, one possible solution to the halo-independent approach is to combine these two. However, inclusion of capture brings two additional assumptions. One is the assumption on equilibrium between capture and annihilation in the sun, and another one is the assumption on WIMP annihilation channel. This complementarity between direct detection and capture was used by Ferrer et al. To develop a straightforward method that gives conservative constraints on WIMP interaction, which is independent of the WIMP speed distribution. This is called halo-independent bounds. However, this halo-independent method was applied to the case of standard spin-independent or standard spin-dependent scenario without assuming any general structure for the WIMP nucleus interaction. Now, non-observation of any new physics predicted by popular extension of standard model, for example, SUSY, motivates one for a bottom-up approach that goes beyond the standard spin-independent or standard spin-dependent scenario. As we know, usually the WIMP scattering process in sun or in direct detection is non-relativistic in nature. So in general, WIMP-nucleon interaction can be parameterized in terms of an effective Hamiltonian that is non-relativistic, and that's why it complies with the Galilean symmetry. The general structure of the Hamiltonian operator is like this, where OIs are the Galilean invariant non-relativistic operator, Ci are the Wilson coefficient, tau is the isospin, and coupling to nucleon can be obtained in terms of the isospin coupling in this way. So non-relativistic operators, Galilean invariant operators for a WIMP of spin half are total 14 in number, which are expressed up to the linear terms in the incoming WIMP velocity. So this list is for all these operators, where operator O1 is basically the standard spin independent operator, and operator O4 is standard spin dependent operator. All these operators are the most general building blocks of the low energy theory. So discussion of halo-independent method is necessary when WIMP-nucleon nucleus interaction is driven by each of these operators to understand the more general scenario that can involve several non-relativistic operators at the same time. Using this operator formalism, one can estimate the differential cross-section of WIMP nucleus scattering in this way, where mt is the target nuclear mass, v is the incoming WIMP speed, and these are the WIMP and nuclear spin, and this is basically scattering amplitude, which can be written in this format in terms of two functions. The function R is basically WIMP response function, which is a function of coupling, incoming WIMP speed, and the momentum transfer. It can be decomposed into two parts, a velocity independent part and velocity dependent part, which goes as this way. The other part is the WIMP, is the nuclear response function, which is basically called the form factor, which is a function of transfer momentum. And this index represents different effective nuclear operators, for example, spin independent type, spin dependent type. And using this differential cross section, one can estimate event rate in a direct detection experiments in this way, where this epsilon is the efficiency of a detector. This is basically the number of target per unit mass of the detector, total mass of the detector, and this is the time exposure. And this rho solar is basically the local density of dark matter. Using the same differential cross section, one can also estimate the capture rate of WIMPs in the sun, where this eta t is the number density of various nuclear target in the sun. And this W is the incoming WIMP speed in the sun, which is enhanced due to the larger gravitational pull of the sun, which is encoded in this local escape velocity term. There is additional velocity cutoff, which is UC max, which is basically the maximum speed up to which capture is kinematically possible, beyond which it is not possible. We also assume equilibrium between capture and annihilation in the sun. That means the rate of capture of one WIMP is equals to the rate of annihilation of two WIMPs. So the assumption is a valid assumption according to the present experimental sensitivity and given the fact that WIMP is the total dark matter. In this case, neutrino signal from captured WIMP in the sun is solely determined by this capture rate. So using all these, one can try to estimate the halo-independent bound on a coupling. In order to do that, one can first estimate the single stream upper limit on a coupling, which is basically the upper limit when all the WIMPs are concentrated in a single stream speed. Let's call it Cmax. So it is a function of WIMP stream speed. So this picture shows an example of the single stream upper limit as a function of WIMP stream speed obtained for a WIMP of mass 100 GeV and operator O1, which is standard spin independent, and WIMP proton coupling. The limit from different experiments are shown. So this is for limit from neutrino telescope, which is based on signal from captured WIMP in the sun. So this is favored for low WIMP speed, where limits from direct detection are more favored for high WIMP speeds. Now, taking a convolution between these two type of limits, the peak value is, let's say, C star. Then one can show that the halo-independent upper limit on coupling square is basically twice C star square. The factor of 2 arises because we combine two different types of experiments which dominate two different speed range. For neutrino telescope experiments, we use ice cube and super Kamiokande, and we also assume that the BB bar is the most dominant annihilation channel of WIMPs, which gives most conservative bound. For direct detection, we use experiments like Xenon 1T, PICO, and PICO with iodine. Now, halo-independent bound is obtained for each pairs of the neutrino telescope and direct detection experiments, and then the most constraining limit is taken as the final halo-independent bound. We estimate the halo-independent bound for WIMP proton and WIMP neutron coupling separately. These bounds are shown as a function of WIMP mass for different non-relativistic operators. Some of these operators, result for some of the operators are shown here. This black line is basically, in each case is the halo-independent upper limit. That means any point above this black line is disallowed by experimental data independent of the assumption on the WIMP speed distribution. For comparison, we also show the upper limit from neutrino telescope and upper limit from direct detection, which are obtained assuming standard halo model. So these are shown just for comparison with this halo-independent bound. In the same way, we obtain halo-independent bound for other remaining operators. So this set of plots are our main result. So in order to understand some general feature from all these plots, we estimate the degree of relaxation of halo-independent bound compared to that obtained for using standard halo model. So for this, we define a relaxing factor, which is basically the ratio between the halo-independent bound on a coupling and the strongest upper limit on the same coupling obtained for Maxwell-Boltzmann distribution or standard halo model. Now, this figure shows the pattern of relaxing factor as a function of WIMP mass for different non-relativistic operator, assuming WIMP-neutron coupling. As you can see, all these operators show some general pattern, that is a moderate relaxing factor in the low and the high WIMP mass region, and in the intermediate mass region, it is relatively larger. I will briefly explain this general pattern. So this set of plots shows the single stream upper limit as a function of WIMP stream speed for 3 different WIMP masses, assuming a WIMP-nucleon coupling for operator, let's say O7. Limits from different experiments are shown, as you know that limits from neutrino telescope, which is based on capture signal, is favored for low WIMP speed, while limits from direct detection are more favored for high WIMP speed. This gray shaded region is basically the WIMP speed range where Maxwell distribution is concentrated. Now, for low WIMP mass, for a low mass WIMP, however, the direct detection is suppressed, but limit from capture can alone probe the full WIMP speed range, and it is rather flat. As a result, the halo independent bound and the bound obtained assuming standard halo model doesn't differ much. So we have a low relaxing factor. On the other hand, for a high WIMP mass, the limit from direct detection can probe a larger WIMP speed range, and it is rather flat in the speed domain where Maxwell distribution is concentrated. So the halo independent bound and the bound obtained assuming standard halo model doesn't differ much. So again, we have a low relaxing factor. However, in the intermediate mass range, as you can see, the limit from direct detection changes very sharply in the WIMP speed regime where Maxwell distribution is concentrated. So the halo independent bound and the bound obtained assuming standard halo model has a large difference. So we have a large relaxing factor. Note that this small relaxing factor implies that the Maxwell-Boltzmann distribution or the standard halo model is not a very optimistic assumption. In fact, the relaxing factor can be as low as a factor of 2 in some cases. The case of WIMP proton coupling is somewhat more interesting. So as you can see, apart from the general pattern that we already seen in the case of WIMP-neutron coupling, here there are some departure from the general pattern, which are mainly observed for in the intermediate mass range for several operators which are spin dependent type. In fact, the smallest relaxing factors are obtained for operator O4, which is the standard spin dependent operator, and operator O7, which is spin dependent with velocity and also velocity dependent. Then followed by other spin dependent operators which have comparatively larger momentum suppression. The reason for this pattern is as follows. Basically, for spin dependent type WIMP proton interaction, the capture rate is strongly enhanced due to scattering of light element hydrogen, which is basically proton, and which basically the most abundant element in the sun. Since capture rate is enhanced, so the limit from capture goes down, and also the C star, which is basically the peak value of the convolution between capture limit and direct detection, also goes down. So we have a small relaxing factor. And this effect is more prominent for operator like O7, which is spin dependent, has no momentum suppression, but in addition velocity dependent. Since the incoming WIMP speed in sun strongly enhanced due to large gravitational pull, the interaction rate for operator like O7, which is velocity dependent, also enhanced. So we have a larger capture rate, so capture limit goes down. So again, we have a smaller relaxing factor, which is more smaller than other cases. So with this, I'd like to summarize that combining direct detection and neutrino search results, we obtain halo independent bound on each coupling of the non-relativistic effective Hamiltonian that drives the scattering between WIMP of spin hub and nucleus. We consider one single coupling at a time. However, it is a first step towards more general scenario involving several non-relativistic operators. For most of the coupling, the degree of relaxation of halo independent bound compared to those obtained for standard halo model is relatively moderate for low and high WIMP mass regime, and this effect is more prominent for spin independent type WIMP proton coupling, which implies that the standard halo model is not a very optimistic choice. In other cases, the limit can be sensitive on the wind speed distribution. So thank you all for your attention.
So do you have any questions?
Thank you for your nice talk, clear talk. So you assume the cellular independent method, you assume the equilibrium between capture rate and annihilation. So if this assumption is violated, in which case this assumption is violated, and what is the impact in that case?
Yeah, actually, let me show you the full relation. So actually, the relation between the annihilation rate of WIMPs and the capture rate is like this. So this is basically the age of the sun, and this is the time scale of equilibrium. Now you can see this ratio it looks like this. So when we have so according to the present experimental sensitivity, the capture rate that we can probe for the capture rate that we can probe, this ratio is much larger than 1. So this tan hyperbolic is almost 1, so we can assume equilibrium, that is the capture rate of 1 WIMP is equals to the annihilation rate of 2 WIMPs. However, in future, if this sensitivity goes down, or on the other hand, the sigma v, which is the annihilation rate of WIMP, which we usually take this value for thermal WIMP, is less, then this assumption is not valid anymore. So one needs to calculate the full equation to transform this annihilation rate to capture rate. So usually neutrino telescope constrains this factor, and we obtain this relation to convert this limit on capture rate and ultimately to the nucleon operator, WIMP nucleus operator.
Any questions? Any further questions? So if there's no more questions, then let's thank speaker again.
Excuse me, how to change light? This one. I would like to thank the organizer for giving me this opportunity to present these works. And today I will talk about the secluded dark sector and Muon G-2 in the light of modified cosmology. And this talk is based on these 2 papers. And this work has been done in collaboration with Ananta Padar and Professor Sougata Ganguly. So as we know that we have enough evidences about the existence of the dark matter, and there exist different production mechanisms in the early universe. So depending on the production mechanism, one can classify the production mechanisms of a particle dark matter as follows. So the dark matter production can be classified mainly under 2 parts, the thermal production and non-thermal. And then thermal production can be subdivided into 2 parts, a symmetric and asymmetric. And the symmetric part can be then classified into some WIMP scenario, which is very well studied. And the SIM scenario, in this scenario, the dark matter is the relic density is set by the 3 to 2 annihilation processes. And the secluded sector, so I will discuss what is the secluded sector and the semi-annihilation process. So today my talk is mostly based on this secluded dark sector scenario. So basically the basic idea of the secluded dark sector scenario is as follows. So suppose we have some visible sector, which is the standard model bath, and we have the dark sector in which the chi is the dark matter candidate and some phi, which is any mediator particle. And the chi and the phi interacts with the visible sector. So basically phi acts as a portal between these 2 sectors. And the main motivation of this secluded dark sector scenario is that it can evade the direct direction constraint. And another thing is that the phi SM interaction is the thermal properties of the dark sector is mainly governed by these phi SM interactions. And in this scenario, that the relic density of the dark sector is determined by this chi to phi annihilation channel. And since we do not know anything about the dark sector, so that can be a multi-component dark sector. That means it can have many particles. and all the masses of all the particles can be same. That means they can be same mass, and also they can be thermally decoupled. That means that these two sectors are not in thermal equilibrium with each other. So in this work we study this thermally decoupled dark sector. So that since we want to study the thermally decoupled dark sector, so we need to solve the Boltzmann equation for the temperature evolution of the dark sector. So basically we have to solve this Boltzmann equation, where this is basically the rate of change of dark sector energy, and this is basically the expansion due to the Hubble parameter. And this is basically the energy injection from the visible sector to the dark sector. So now if we assume that the dark sector is internally thermalized, so one can write the rho prime is proportional T prime to the power 4, and defining xi as a T prime by T, one can write this parameter xi as a function of the standard model bath temperature. So in this work, we have considered a U1 LV minus L tau times U1 X extension of the standard model. So the U1 LV minus L tau is very well motivated scenario in case of to address the muon anomalous magnetic moment anomaly and the neutrino mass mixings. And in our work, the dark sector is charged under U1X gauge symmetry, and the Z prime gauge boson, which is the gauge boson corresponding to the U1X gauge symmetry, is kinetically mixes with the LV minus L tau gauge bosons. So therefore, in our scenario, that the dark sector, the Z prime couples with the muon and tau flavored standard model leptons. And another thing is that since the Z prime is coupled with the muon and tau flavored leptons, so therefore the phenomenology of this model is less constrained in comparison to the gauge B minus L scenario, where the dark sector is directly coupled with the first generation of standard model leptons or the standard model quarks. So here is the Lagrangian we started. So basically LSM is the standard model Lagrangian, and this is the kinetic term of the dark matter, where chi is our dark matter. And the last term, we introduced the kinetic mixing between this F mu tau and X hat, where the F mu tau and X hat is basically the field strain tensor of the U1 LV minus L tau gauge symmetry and the U1X gauge symmetry. So now if we diagonalize this Lagrangian, one can see that the mu and tau flavor leptons are coupled with this Z prime with the coupling epsilon. And I will define what is the epsilon. So basically this Gx is this Gx parameter will determine the dark sector freeze out, and epsilon, which is a combination of some different parameters in the original Lagrangian, and it basically determines the energy exchange between the two sectors. And we are interested in a scenario where the LMU minus L tau gauge boson is much heavier in comparison to the U1X gauge boson. So therefore we have 4 free parameters. It is the M, which is the dark matter mass, epsilon, this is the total coupling, Gx, and Mz prime. So now we have to solve the Boltzmann equation to calculate the relic density of the dark matter. So in the left side, this is basically the co-moving number density of the Boltzmann equation as a function of the rate of change of co-moving number density, and X is defined as the M chi over T. And this term is basically the dark sector freeze out term, where the temperature evolution of the dark sector is encoded in this Y equilibrium function, which is basically the T prime. And there is another term which is basically the freezing term, where the standard model particles annihilates and produce the dark matter, which is basically the freezing term. So here is the evolution of the relic density with respect to the parameter X, which is X is defined as M chi over T. And one can see that for the black line, for which is the alpha X is very small, which is defined as the Gx square by 4 pi. And the relic density is mainly governed by only this term. And as we increase the value of the alpha X, so there is the freezing term will trigger, and the final relic density will be governed by this blue dashed line. And if we further increase the value of alpha x, then we will find that the dark matter is excess amount of dark matter is produced from the standard model bath, and then it will reannihilate into the Z prime to set the final Rayleigh abundance. The similar behavior can be obtained from these choices of parameters. So now here is the m chi epsilon plane. So the main message of this plot is that the dark sector Rayleigh density is satisfied in this region, but the epsilon value is very small. And the WIMP next door is basically the parameter space in which both the sectors are in thermal equilibrium. So one can see that the dark sector Rayleigh density is satisfied for very small values of epsilon. So recently it was reported that there is a deviation between the standard model prediction and the experimental observation between the anomalous magnetic moment of the muon. And since we are in the regime where the Z mu tau is very heavy, so there is the only one solution, only one possibility to solve this muon G-2 anomaly is from this diagram. So we would like to address the question that is it possible to reconcile both this the dark matter Rayleigh density and muon G-2 in a uniform framework. So to do that, we use the idea of a fast expanding universe. So the idea is as follows. So suppose we have some phi component which redshifts much faster in comparison to the standard radiation, and we define a temperature Tr at which rho phi Tr equal to rho rad Tr. That means that at Tr both the energy densities are same, and we choose the Tr to be such that at the time of BBN, our universe should be dominated by this rho radiation. So if we use the entropy conservation, so one can arrive at this relation where the rho T is function of the rho R as well as this non-trivial dependence of the T over with N. And for a large values of T, basically the Hubble parameter is much larger in comparison to the standard Hubble parameter. So now we will solve the same Boltzmann equation. So basically with this Hubble parameter, we try to check whether what is the parameter space in which the dark sector is not thermal equilibrium. So as we can see, for a large values of m chi and the epsilon roughly 10 to the minus 3, there is a parameter space in which the dark sector is not in thermal equilibrium with the visible sector, but there is some free parameter space in which the dark sector is thermally decoupled, but that it can satisfy the muon anomalous magnetic moment. So now we need to study the Rayleigh density, in which we solve the can we satisfy the Rayleigh density constraint for epsilon 10 to the power minus 3 in this parameter space for large values of m chi. So now we solve the Boltzmann equation again with the modified Hubble parameter. So this is basically the modified Hubble enters into this equation, and again we will see for n equal, we choose from n equal to 3, and one can see that for small values of alpha, the dark matter is mainly produced by a freezing mechanism, whereas if we increase the values of alpha, so excess amount of dark matter is produced from the thermal bath, and since then they annihilate into the Z prime, and then finally sets the Rayleigh density. So similar behavior can be obtained for n equal to 4, and one can see that the dark matter is produced from this thermal bath, and then since the Hubble parameter is really very large in this regime, because in this regime the phi components dominate the Hubble parameter. So the annihilation rate of chi to Z prime is not sufficient to annihilate chi into Z prime, but as x approaches XR, the Hubble parameter decreases and the annihilation rate starts again, and finally the dark matter Rayleigh density is satisfied. So now this is the parameter space for the m chi epsilon plane. So the basic scenario, the main message is that the dark for n equal to 4, the dark sector is in thermal. This is the region in which the dark sector is in thermal equilibrium, And one can see the relic density satisfied region here. And we show that for two benchmark values of mz prime and for two benchmark values of mz prime, the epsilon for fixed values of epsilon, it is in the parameter space in which the g minus 2 and relic density is satisfied. So here is the L mu minus L tau constraint for standard cosmological scenario. And we want to show that if one can satisfy this relic density constraint in this region, and in the modified cosmological scenario, we find that it is indeed possible to satisfy the relic density constraint while satisfying the other experimental observations. So here is the conclusion. So the U1 L mu minus L tau times U1x is a well-motivated gauge extension in the context of standard model in muon anomalous magnetic moment and anomalous magnetic moment and neutrino mixing. And we find that since the L mu minus L tau portal is not coupled with the first generation of leptons and the quarks, so therefore it is less constrained. And finally, we showed that for a modified cosmological scenario, it is satisfied. It is possible to satisfy the muon g minus 2 anomaly and the relic density constant if we consider a fast expanding universe in the early universe. So thank you.
The question time. Yeah, do you have?
You introduced gauge kinetic mixing between these new gauge bosons.
Yes.
So in principle, this X, U1X could have gauge kinetic mixing with the standard hypercharge.
Yes.
Have you considered that possibility?
So yes, basically we have considered it. So since you are saying that the gauge kinetic mixing between the U1Y and U1X, right? So if we do not consider this at the tree level, but it can induce the loop level mixing between the Z prime and gamma and the Z. So that we have considered because these bounds, so basically the white dwarf bound is basically the E plus E minus the plasmon decays through standard model neutrino. So basically the E plus E minus 2 annihilates to, if one can imagine that the E plus E minus 2 to the gamma, and there is a loop, and then Z prime, then two neutrinos. So we have considered this loop-induced mixing. Yes.
Any other questions?
So I'm curious about this BBN bound.
Yes.
So that's can you explain what the BBN bound?
Okay, so this one is
no, it's there is a dashed line.
Okay, so I will explain. So dashed line is basically we just show that in this region of parameter space, the Z prime can be in thermal equilibrium with the standard model neutrino bound. But this bound is basically that it will directly contribute to the delta n effect for Z prime roughly 5.5.
Okay.
So that's why we show the BBN bound as this, but we also show that in this region of parameter space, the Z prime in thermal equilibrium, but it will not contribute to the delta n effect because the mass is very high.
Okay. So what kind of bound?
Sorry.
So how do you?
Okay, so basically we calculate the rho Z prime.
Rho G prime.
Rho Z prime. And then the delta n effective equal to 8/7, 11/4, 1/3 rho Z prime by rho gamma.
Yeah, but there's delta n effective bound, right?
Yes, that's it.
Okay, so I'll explain.
Okay.
Any other questions? If not, let's thank Sougata again, and let's thank all the speakers of this session again.